Now, our speaker. Some of you may have seen this issue of the City Pages last April, that we have an astronomer in Antigo, of all places. And not just any astronomer. We have an astrophysicist, biologist, astrobiologist up in Antigo. Well, she's also down in Madison a bit, too. Dr. Margaret Turnbull is our speaker today from the Global Science Institute. And she'll be talking about, will there ever be another Earth? The last 20 years has taught us so much about planetary systems, orbiting other stars, and these discoveries bring the question, are we alone? Into much clearer focus. Dr. Turnbull is an astrobiologist whose expertise is identifying star and planetary systems that are capable of supporting life as we know it. She now works with the NASA chartered team to develop a concept for a starshade observatory to find and characterize Earth-like planets among the nearest stars. Turnbull will describe what we've learned so far about planets and life and how we will get to the next level. Dr. Turnbull received her undergraduate degrees in astronomy from UW-Madison, so that's my alma mater, and many of us here, an MS and a Ph.D. in astronomy with a minor in cell biology at the University of Arizona. I guess she wanted warmer climates for a while, huh? When not thinking about star shades and life on other worlds, she can be found keeping honeybees, tapping sugar maples, and cross-country skiing in the northwoods. So she is an Antigo person. We welcome Dr. Turnbull.
Good morning. Good morning. Thanks so much for coming out. I just admire all of you for, who cares if it's minus 25? We're tougher than that. We've seen worse. So thanks so much for coming. I'm really happy to be here today. Talk about the question of will there ever be another Earth, and also introduce a concept for a next generation of space telescope observatory that will be designed to answer that question and actually search for Earth-like planets around the very nearest stars. I'm going to try not to... Maybe if I step away from that microphone. I'm not sure. Can you still hear me if I stand over here? Okay. I noticed that. Yeah, I'm going to try not to do that. Okay. Well, I like to begin all right, so actually, certain things I have to get out of the way first. I have to follow up on a conversation I was having this morning right here. How many people in this room are currently sitting in the seat that is identical or almost identical to the seat they sat in last time? Okay. I do the same thing. And I was actually remarking that I read at one point that is a smart thing to do because, evolutionarily speaking, every time you get in a new situation, you need to map out all the variables mentally. You need to know what all the threats and opportunities are in the situation where you're at. So by sitting in the same place every time, what you're doing for yourself is alleviating all those concerns because you sorted that all out on the first day. And now you can just pay attention to the slides. And it's actually been recommended for students, if there's anybody here who teaches or advises students, if you want to just learn the most and do the best on final exams and whatnot, sit in the same seat you sat in, last time. So just a thought. But, sometimes we think we're just creatures of habit for no reason, and sometimes there's a good reason for it. But anyway, I like to about the Earth with this image here. Does anybody know where this image comes from? This is the first widely published image of the whole Earth. This actually comes from the Apollo mission. And does anybody know which one, perchance? It was one of the later ones. I actually don't know off the top of my head. I do know this, but these are things that I forget quickly and have to relook up every day. But the Apollo astronauts in one of the Apollo missions finally had an opportunity to snap this photograph from the spacecraft as they were leaving Earth, because the Earth and Moon and Sun happened that time to be all in a line. So on their way to the Moon, the Sun was in front of them, and they could turn around and get this view of the fully illuminated Earth. And when this image was downloaded, there were 1 billion people who saw their home planet for the first time, and in full glory, suspended in just the emptiness of dark, apparently infinite space. And you can think about how an image like this, I actually have it here oriented in the same way that it was originally downloaded, which is, quote unquote, upside down, compared to the way we're used to looking at the Earth. But of course, in space, there is no up and down. This is the way that they saw it. But you can think about how an image like this then went on to become the most widely reproduced image in history. And for a long time, this was it. This was the only image of the Earth, fully illuminated Earth as seen from space. And you'll recognize it. If you look at this, you can sort of memorize these cloud patterns, and you'll recognize when you're seeing the original image because it's the same. But yeah, so this, and then, this became sort of the poster child image for the environmental movement going forward from that era. The Clean Air Act, the Clean Water Act. It was very inspirational and just incredibly impactful, just visual summary of what we're talking about when we think of a habitable planet and life in the universe. Trying to understand this planet is going to be the work of many, many generations up to this point and going forward. Understanding how our climate works, understanding how life interplays with the planet in order to keep this planet habitable for us, understanding all of the free services that we get from a healthy environment in terms of purifying our water, keeping the atmosphere habitable for us. The whole life support system of the planet is very complex, and you don't get to just harvest one variable out of it without affecting that balance in some way. So our challenge going forward, for my generation, future generations, is to figure out, given the kind of lifestyle that we want to live, given the basic needs that we have in order to do these bigger things, explore space and so on, how can we set up our society in such a way that hopefully the day will come when we're not living in fear about what we're doing to our own planet. But we have a lot of learning to do to kind of get to that point. And I feel like there shouldn't be a trade-off between, living well on a planet and also living for a long time on a planet. So the question is, for me anyway, are we really alone? That's the one habitable planet. That's it. We're done. This is actually an image not of our own galaxy. This is an image of the Andromeda Galaxy, our big sister spiral galaxy. I show it because it's very similar to our own. And Andromeda is actually on a collision course with the Milky Way galaxy. But we don't have to worry about that for a while. But it's interesting to think about. Some of my colleagues have modeled this, and it does make quite a spectacular display when that happens. Interestingly, there are about 400 billion stars in this galaxy, similar to our own. 400 billion, it's a big number. It's a number that I don't think anybody can really comprehend. That's a lot of stars. But interestingly, when two galaxies like this collide, very rarely, like maybe only once or twice, will the individual stars actually run into each other. There's so much empty space between all the stars that they just sort of slide right through. And eventually their gravitational wells just sort of all combine into a bigger galaxy, probably spheroidal in shape. But it's interesting to think about how much empty space there really is in the universe, even in these, I have to do something about that. Okay, so even in these, really elaborate structures and that seem like they're just so full of, of things, it's actually mostly just empty space there. But anyway, there's 400 billion stars here. You can also see other stuff in here these dark lanes here, if you could sort of rotate this galaxy and see it face on, it would look like kind of a spiral structure. And then if you look at it edge on, it just looks like a line, really. It's a disc-shaped galaxy like ours. And all the stars in the universe are born out of these dark clouds of gas and dust. It's almost like they're condensing. It's not exactly like rain clouds, but it's very similar. These waves, these pressure waves, are sweeping through the galaxy and compressing all this dust and gas. And when that happens, some of that dust and gas begins to just contract under its own gravity and form new stars and new planetary systems too. So that's ongoing all the time in these spiral galaxies. And stars are, stars come in a great variety of kinds. Not all stars are the same, so I'll get to that in a second. Here's the Andromeda Galaxy on the sky. If you had ultraviolet eyes, you would be able to see. This is about the right size of the galaxy compared to the full moon in the sky. So it actually extends. It is a naked eye object. You can see it. You wouldn't be able to just with your eye make out this whole full extent of it, but you can sort of see a fuzzy blob, right here. But it's interesting just to think about that. If our eyes were more tuned to this, the kind of things we would be able to see in our nighttime sky. So 400 billion stars sitting right there in that one little patch of sky. What I've just done is made a tiny little red box appear right here. If it's hard to see, then that's appropriate because it's very small. And it's only, but the size of this little red box right here actually corresponds to an image that the Hubble Space Telescope took, which was the key project of the Hubble Space Telescope. The whole purpose of the Hubble Space Telescope, in addition to enabling many kinds of new science, but the key project was to stare at one little tiny patch of sky like this for about a month and use all that month of exposure time from space to see what was there. And many graduate students pored over the sky to find a tiny little patch of it like this that had, as far as we could tell, nothing in it at all. And so Hubble's task was to stare at that little patch of sky and see what there was. So when Hubble did that, this is an expansion of that little patch of sky. It's the location of that patch of sky is not necessary. It's not really right next to the full moon. Anyway, the moon moves all over the sky, so that location means nothing. I'm just giving you a relative size here. So if we zoom in on that little patch of sky with Hubble Space Telescope, this is what came back. So prior to this image downloading and coming back, there was nothing, as far as we could tell, in this patch of sky. And what's interesting about this is that there are no stars in this image. These are all galaxies. These are all Andromeda galaxies. Every single speck of light you see in here represents another 400 billion some odd stars, right? And the amazing thing about this is, so since then, this was done a couple more times. And the interesting thing is that it doesn't matter which direction you look in, similar situation comes back. So this is just that one little tiny little patch of sky. There are as many galaxies in the visible universe as there are stars in any individual galaxy. So imagine, 400 billion times 400 billion. That's about how many stars we're talking about within our visible universe. And by that, I just mean the horizon out to which we could conceivably see. And there is no indication that the universe is actually finite in size. And so our little bubble of the universe that we can currently see. So anyway, a lot of stars. So let me explain that. When you're looking at a little patch of sky like this, what you're doing is you're looking down a little pencil beam. So everything as far out, as can be seen to the edge of the visible universe in that little patch of our sky is here. So some of these galaxies are nearby. You could sort of imagine this in 3 dimensions. So I don't know this for sure, but I could make an educated guess here and say that the galaxies here where you can actually see some structure, like some spiral arms, these are nearby. And we're looking through kind of a tunnel of space here, and all these tiny little specks of things that you can kind of barely see, that's not noise. Those are actual galaxies. They're just very far away. They're much farther away. So imagine like this galaxy right here, and that little speck right there being very much the same, but this one's close by and that one's way far away. If you could sort of imagine that 3-dimensionality in this image. So yeah, good question. Stars, okay, so that's the situation with the number of stars we're talking about. Now, what about all the different kinds of stars? Because they're not all the same. Stars are not all the same. In fact, there's no 2 stars, really, that are the same. We've looked at a lot of stars now, and there is, the search for a solar twin, a solar twin, that's actually a phrase that astronomers use, the search for a solar twin. We have, a list of so-called solar twins, but every one of them is actually different from the sun in some way. There's just so many different aspects to a star, a given star's personality. There's really no such thing as a twin. And which kind of gets at my question about will there ever be another Earth? That's food for thought then as we go forward in this. But I wanted to just talk about habitable zones for a second, because when you're talking about, why can we live on this planet? It's the right temperature, and space is very cold. Space is 3 degrees above absolute zero, and it makes this outside right now, this is comfy, and that's nice. That's nice compared to the emptiness of space. And when I'm coming back from a long ski, because right now I'm training for the Berkey, and I always end up coming back in the dark, and I always end up coming back in the moonlight. I was skiing last week, and I came back, and by the time I got back to the lodge, it was 2 below, and who knows what the wind chill was. But on my way back, I looked up, and it was just crystal clear, which we hadn't had, crystal clear skies in quite a while. But I was looking, and all these stars are shining like through the branches and stuff of the trees, and I just thought, it's not very far to outer space from here, and space, literally outer space is like 20 miles that way. It's not far. We're under this most tenuous, thin little blanket keeping us warm. And when it's that cold outside, you can sort of appreciate like how tenuous that protection is. But because space is very cold, and it's not, the coldness of here and the coldness of space, they are related to each other. You need a star to keep you warm in space. And so all the habitable planets in the universe, I can say this with some degree of confidence, maybe with a few exceptions, are huddled in close to a star out there. You think of these stars as little tiny nuclear furnaces scattered throughout this incredibly cold universe, and planets are in orbit around them. They form with the star, and whatever that planetary system is like, the planets that are the closest to the star are the hottest, and the ones that are furthest away are the coldest in that system. And somewhere in there, there's a sweet spot, which we call the habitable zone, like the Earth, to actually have liquid water running around on the surface. And if you took the Earth and you moved it farther out past Mars, say, we would end up with a situation more like Europa, where the oceans would be completely, permanently frozen over, and possibly frozen solid all the way through. And, there are a couple of really interesting moons in our own solar system, like Jupiter's moon Europa, which appears to be
have much larger oceans even than ours. Generally, as you go further out in the solar system, there is more and more water on planetary bodies, but it's frozen, out there because it's cold. But Europa, Jupiter's moon, is in orbit around Jupiter, and it's continually being massaged by tides, really strong tides from Jupiter, and that generates enough heat to keep the interior of it liquid, even though the outside of it is frozen. So it's kind of this frozen shell floating on a vast saltwater ocean, and we know that it's salty because we can detect the circulation of those currents in the magnetic field of that moon. So it's a very interesting place. That's probably the most interesting place in the solar system from the perspective of life, second to the Earth. Anyway, there are exceptions to this, but the Hab zone is a place where an Earth-like planet could have liquid water right out on the surface, which for me as an astronomer, I know that not all life lives on the surface. In fact, most life, even on Earth, lives underground or in the oceans. And of that, most of it does live actually underground, like in the soil, not even in the oceans. But what I like about water on the surface is that it means you can have life forms on the surface, and it means that I might be able to see it then from far away without actually going there. Planetary scientists have this luxury of being able to send probes to their planet that they study, like Mars, and eventually Europa. That'll be in the next generation here. Europa may get a lander or something, but they can actually go there and dig down and study the soil. We can't do that as astronomers. We have to look at everything through remote sensing. And so the idea of life on the surface, that is very appealing. That's what we're going to target first, only possibility. But brighter stars than the sun, intuitively, have habitable zones that are a little further out. And fainter stars than the sun, also intuitively, have habitable zones that are close. This looks like such a simple graphic, but actually there is like a ton of astrophysics in this. And just to be able to make this slide requires so much information. But what's interesting here is that stars that are more luminous than the sun, their Hab zones are further out and they're actually physically wider. So you could fit more than one planet in the Hab zone of a more luminous star than the sun. Conversely, these little faint red stars, their Hab zones are closer in. They have narrower Hab zones, and maybe just one planet at the most would fit within there, maybe. But these guys here, these little faint red stars, they are the most numerous stars in the galaxy. 85% of the stars in any galaxy are these little faint red stars. And you cannot see any of them in our nighttime sky. They are so faint. The very closest star to the sun is one of these little faint guys. It's Proxima Centauri. And it's only 4 light years away. You will never see that star with the naked eye. You will see it with a telescope, but not with the naked eye. They are so faint, but they're so numerous, and so most of the Hab zones in the galaxy are around these faint little guys. And the other thing about them is that they burn through, even though they don't have as much fuel to burn in nuclear fusion with burning hydrogen, they burn through it so slowly that no red dwarf, we call these red dwarfs for all kinds of perfectly logical reasons. We call them red dwarfs. No red dwarf has ever run out of fuel to burn. So the oldest stars in the galaxy that are still burning hydrogen are all these little faint guys. And these will just sit there stably burning hydrogen, remaining the same brightness and the same temperature for a trillion years. I mean, much longer than the current life age of the universe. So these guys are incredibly stable and very, very numerous. On the other hand, these brighter stars, even though they have a lot more fuel to burn, they burn through it so fast that really, by the time planets are done forming in these systems, this star is already running out of fuel to burn. It's already starting to swell up into a red giant. I won't go through the whole life cycle of stars, but they start out like the sun burning hydrogen. And when they run out of hydrogen, they start burning helium. And when that happens, they swell up into a completely different state. And it's a much larger state. You know, when that happens with the sun, it will be, you know, it'll be large enough to actually, you know, the Earth will be in orbit inside of it. So, you know, that'll be kind of the end of days for us here. And we'll have to go move somewhere further out in the solar system. But, you know, but so these guys, even though they emit most of the light in the galaxy, they're so bright, you know, there are very few of them. But when you see that picture of the Andromeda Galaxy, what you're seeing is primarily light from these guys, even though there's so few of them. They're the ones that do all the shining. I'm going to tell you one more astrophysical thing that's of interest here. These guys are the ones that have made life possible in this galaxy. And you're thinking, well, how is that possible? I mean, life can't even get going before they die. But what happens with these guys is that, so they swell up, they become a red giant, they burn helium for a few minutes, and then they explode. I mean, then they run out of helium, and then they just explode. But in the process of that explosion, the physics of that actually creates all of the other elements. When the universe was born, it did not have anything in it in the way of hydrogen, nickel, silicon, all these heavier elements that are so essential to us in even forming planets at all, you know, let alone planets with life on them. Carbon, oxygen, nitrogen, I mean, these are all crucial. These are the building blocks of life, and they didn't exist early on. The first generation of stars had nothing in them other than hydrogen and a little bit of helium. But these massive stars, when they formed and died and exploded, and that explosion created all of those elements that then got distributed in the explosion throughout the galaxy and then formed into stars, into future generations of stars. It became part of all that gas and dust that I was talking about that then condensed out into new stars and the first planetary systems. So these guys have an important role to play in the evolution of the galaxy and the habitability of the galaxy to life. All of this fits together. The story, this is the harmony of the spheres that I'm describing to you here. Everybody has a role to play when you're looking at the universe through the lens of life. And then even within a certain class of stars, like sun-like stars, all of them are different. This is just a, you know, kind of an interesting picture of a solar flare, but you know, they really just don't flare at all. The sun, even though, you know, this looks like pretty massive, and it is, the sun is actually a fairly quiet star. Most stars are a bit more active than the sun, so they've got a lot more of this kind of activity going on all the time. And there's other things about stars that can be different from each other. For example, let's see if I can, yeah, good. For example, you know, the sun is a single star. It's a single star, and it has its little family of planets and comets and asteroids and stuff. That's very nice. It's a nice picture. But most of the stars in the galaxy are not single. Most of them are in double systems. We call them binaries, or triple systems, or quadruple or more. Some of them are in huge clusters. We call them globular clusters of 100,000 stars or more, all in a big swarm. So what does that mean? You know, this image right here is of Alpha Centauri. This is the nearest sun-like star to us. The brighter one is Alpha Centauri A. It's a star very similar to the sun. And this is Alpha Centauri B, a little bit fainter, a little bit redder. And this little circle right here is showing where Proxima Centauri is, that little red dwarf that is actually the closest star to us right now. So these stars are all gravitationally bound to each other. These two orbit each other once every several decades or so. And Proxima Cen is much further out. So we're looking at thousands or 10,000 years for Proxima Cen to go all the way around this whole system. But it's 3 stars there. And from the point of view of an astrobiologist, there's different ways I can look at this. I can say, okay, well, yeah, it's different from us, but this is now 3 opportunities in one place for habitable planets to exist and for life to get going. And how interesting to think about if we had a second star in orbit with the sun and it had its own planetary system. Man, would that not be so fun to be able to explore that and spread? Or maybe it would have had habitable planets in its habitable zone and its own little system of life that we could go over and destroy. Oh, just kidding. Go over there and and learn from, and learn about. I mean, how interesting would that be? In fact, I used to work. I actually got my start in graduate school working with SETI, the Search for Extraterrestrial Intelligence. How many people have seen the movie Contact? Well, Jill Tarter, my graduate advisor, is the woman that the Jodie Foster's character was based on. That's a whole other really interesting story. But binary stars are of interest to SETI for that reason, because you think about spending your precious telescope time, searching for signals 1 star at a time. How nice if you can get 2 at once. And especially if there's a possibility of 2 civilizations around each one and they might be talking to each other, and that might, some of that might leak in our direction and make it more favorable for a discovery. So anyway, multiple systems, that's a variable. The temperature, we talked about that. The luminosity, the brightness of the stars, they're very different. Some stars are loud, some stars are quiet. With flaring activity. Some stars are, they're different ages. They'd have different amounts of metals like iron and silicon and whatnot that we can see in their atmospheres, and that probably means that that's how much material was available to form planets and so on. So we like to know all those things about stars in order to figure out, where to search for habitable planets. So I want to tell you, I can't talk about this without, making sure that you know about NASA's Kepler mission. How many people have not heard about NASA's Kepler mission? This is typical, yeah. Maybe I would say typically, an interested audience, maybe a third of people will have heard about it and heard especially in detail about it. But the idea is this. So NASA launched several years ago a small space telescope to stare at a certain patch of sky that was just, from our perspective, very dense with stars. And again, you're looking down at a tunnel of stars. So some are nearby, some are far away. But there wasn't a lot of dust and gas in the way, and we could just see a lot of stars. And just for 4 years, its purpose was to stare at that one patch of sky and monitor the brightness of every single one of those stars. And, you can imagine this telescope, in orbit around the sun. And the whole time it just stays, pointing at this one little patch of sky the entire time without moving. And it was actually quite an accomplishment for the engineers that made that happen. But the purpose of it was to see if out of all those stars, any of them might have planetary systems that were oriented edge on from our perspective, so that when the planet would pass in front of its star from our perspective, we would not be able to see that planet, but we would be able to see the brightness of the star getting a little bit dimmer while the planet was in front of it. And then when the planet continues on its orbit here, the brightness of the star goes back to what it was before. So Kepler's job was to do that for this patch of sky right here. There's about 100,000 stars in this patch of sky. These are all in our own galaxy, relatively nearby in the grand scheme of things, within a couple thousand light years. And see, I think I have another graphic here sort of showing. So if the sun is here, this is a drawing of our own galaxy. Of course, we can't see it from that perspective because we're inside of it. But this is approximately what it would look like. So the sun is here and Kepler is staring off in this direction. Getting all of these stars that are in this little cone out in that direction. And it's about 100,000 stars or so. And what it came back with, and feel free to ask me more questions later about how that all works, but the gist of it from my point of view as an astrobiologist is in that field of observation, that field of view that Kepler was looking at, what it found was a whole ton of planets that happened to be in edge-on orbits. There's many, many more planetary systems in this field that we can't see because they're going around the star like this. From our perspective, they never pass in front of their star as seen from Earth, so we can't detect them this way. But they're there. I mean, they're there. It's all randomly oriented. It's not, there's no favored orientation of planet orbits. But what came back is all the blue dots here, these are all discoveries of Earth-sized planets. All the green dots here are what we call super Earth-sized planets, so maybe 1.5 to 2 times the size of the Earth. And then all the orange dots here are Neptune-sized things. Neptune's about 4 times the size of the Earth. And then all the red dots here, these are all giant planets. What's so interesting about this is that nobody was expecting this. Every time we study anything, it's always something we're not expecting comes back. But these super Earth-sized things, in between the size of Earth and Neptune, are like the most common kind of planet in the universe, apparently. And we don't have one in our own solar system. And we don't know what that is. We don't know what it looks like. Is it like the Earth, only big? Or is it like Neptune, only small? And does it have a surface that you could walk on? Or does it just have an atmosphere that just gets denser and denser and denser and denser as you go down, like a gas giant? What are these things like? So very interesting that that's turning out to be the most common kind of planet that there is. This is sort of showing a tally of discoveries. So these are Earth, super Earths, Neptunes, Jupiters, and supergiants. And it looks like the Neptunes are the most common here, but as time goes on, looking at this data, this is the category right here that's growing the fastest. These guys are the easiest ones to find, so we sort of found them all right away. And then now with more and more data, this column right here, we are finding more Earth-sized things too. But it's this super Earth-sized category that's growing the fastest, and just extrapolating, we can tell that this is like the most common kind of planet that's out there. So it's really interesting. Of course, these planets aren't necessarily going to be habitable. Just because they're Earth size doesn't mean that they're the right temperature. And because they might be, actually it's much easier to find them this way if they're very close to the star because they're going around much faster. And so you can see that happen many times, and then you're more confident that that's real. And astronomers always need to see things 3 times before they say that it's real. It's just sort of like that's the industry standard. And even then, we still like to have it followed up and detected in some completely other way as well in order to really truly confirm that that's a real detection. Pretty rigorous. We don't give ourselves a lot of breaks here, but we say now it looks like just extrapolating from that one field of sky to the rest of the galaxy based on what we know about those stars and the rest of the stars in the galaxy, it would appear that about 1 in every 5 stars has an Earth-sized planet in the habitable zone. So we're talking 20%-ish of 400 billion stars in our one galaxy. And there's a lot of factors that went into making this planet habitable, not just size and temperature. Size and temperature is a good start, but you had to have water delivered to that planet from further out. Our water doesn't just come from here. It comes from asteroids and comets that impacted the Earth long ago when the Earth was first forming. We can tell that. We can tell that by the balance of deuterium and hydrogen in our oceans, that it matches up with comets and asteroids really well, much better than asteroids that are closer into the sun. Way for water to get delivered to that planet. Maybe there are other important factors too that play into whether that planet can be habitable. We had a huge collision with a Mars-sized planet early on that formed the moon. and removed a whole bunch of the Earth's outer crust, which, maybe is what has made plate tectonics possible on this planet, which then circulates the atmosphere and, keeps things from getting too hot or, too many greenhouse gases in the atmosphere or not enough. And so that's, there are a lot of things that go into this, but this is still a great start. Size and temperature, I'll take it for right now, till I can learn more. These planets could actually be habitable. Kepler 186f, that's the first Earth-sized planet in the Hab zone. It was all over the news. It was like Earth 2.0, Earth's twin. It's a shadow that passes in front of a star. Right now, that's what we know about it. But we can guess at the size and temperature and say that it might actually be very similar to the Earth, at least in that regard. And what they don't sort of tell you in the media typically about this is what kind of star it orbits. This guy orbits in one of those red dwarfs, intuitively, because red dwarfs are the most common thing that there is. So most of the planets that we're finding are in orbit around those little M dwarfs, red dwarfs. And the thing about these red dwarfs is their Hab zone is so close to the star that if that star flares at all, singe the surface. If the planet is almost certainly going to be tidally locked to the star. So the same way the moon is tidally locked to the Earth, we always see the same side. Planets, you would always have one side that was daytime and one side that was nighttime. And you wouldn't have, like a 24-hour day like we have here. So one side's going to be hot, the other side's going to be cold. And what happens is that climate can become very unstable. You end up with this scalding desert on one side, and all of that water is evaporated and ends up freezing out on the cold side. So you've got a ski hill and a desert. Those are your choices for getting life going on that planet. I don't know if red dwarfs, even though they're so common, I don't know if we should count them or not. And so many of my colleagues are having an absolute love affair with red dwarfs because there's so many of them. But I just feel a little more reserved about that. I feel like you got to make some leaps there to say that these could be habitable. But I just came from a huge conference there last night in Seattle. We had this massive convergence, like we do every year in January, of all the American astronomers and half of the rest of the world's astronomers too come to this thing. There were thousands of astronomers there, and there was a press announcement yesterday morning that I went to, and they announced 3 new planets discovered by this Kepler mission that are actually in orbit around sun-like stars, and they are approximately the size of the Earth. One of them in particular, very close, about 30% larger than the Earth, and the other 2 are less than about twice the size of the Earth. But all 3 of these are orbiting sun-like stars, and all 3 of them are orbiting in the Hab zones of those stars. So very interesting. They're going to be a challenge to follow up on, but I know that my colleagues will be really following up very closely on all 3 of those to whatever extent possible. So the question is, how can we learn more about them? How can we find out if they're actually alive? Here's this is where my work comes in, and I just want to take a picture of the planet. A shadow isn't good enough. A shadow is great to find a lot of them and get some statistical information, just about how many there are. But I want to find planets around the very nearest stars to us, the brightest ones, and actually be able to see light coming from that planet and study that independently. So I want to see a pale blue dot that I can look at and actually tell if there's water, clouds, continents, plants, and so on. This is how we do it. We have to take an image, a real picture of the planetary system. This is currently the state of the art. This is a fairly nearby star, and this is the only really well-imaged planetary system. It happens to be face-on. This time, face-on, then now that's what you want if you're trying to take a picture. Yeah, okay, is that 5 minutes? Okay, great. And this is kind of the state of the art, but these are all giant planets, and they're way far out from their star. This right here, this is already 20 times farther away from that star than the Earth is. So if you imagine the Earth is like buried down in here, and this star has been removed from the image so that you can actually see those planets. And you can imagine how much harder that's going to be to try to see little tiny, way smaller planets right down in there. So we have to design a new, so this is kind of my dream, I want to be able to, this is a picture where the star has been removed. Everything shining in here is either a planet or dust. We have a lot of dust in our planetary system. So this would be Neptune out here, and Neptune is sort of shepherding around a bunch of this dust, so you can tell it's there. But then when you zoom in to this little inner region, you see this is Saturn out here in Jupiter. And then Venus and Earth are in here. Mars is just too small. You can't see it. But once I have that little speck of light coming from Earth, then I can begin to study that, and I can at least make inferences about what that planet might be like. And so, even though it's just going to be a tiny little dot, this is Voyagers' image of the Earth turning, this is taken not even from that far away, and it's just a pale blue dot. I can break that dot of that point of light up into all its different wavelengths. I can see what it looks like. How bright is it in the blue? How bright is it in the red? How bright is it everywhere else? And from that information, I can tell if there are things like plants, clouds, continents, and so on. This is a movie of the Earth being passed by from the Messenger mission on its way into Mercury. And if you just squint at that and imagine that's just a single point of light, you can imagine that the brightness changes over time and the color changes over time. And that's what tells me that the Earth is turning and that it has stuff on the surface that, might be interesting to know about. So how to actually make an image like that, what I showed you was was an artist's concept. We need to fly a mission like this, and I'm going to show you what I've been working on. This is a small space telescope flying in conjunction with what we call a starshade. It's a gigantic, very carefully machined piece of plastic, basically, that just flies in front of the telescope. And I have a little movie here of how this would go. They can launch together. They go up into space. They separate. The starshade deploys. This telescope points at it, and then the starshade flies in front of a nearby bright star. There's a ton of engineering that goes into this starshade, but it's actually very sharp. We have we have models of it, and it's actually dangerous holding these things. And then, they block out the light of the star so that you can actually see the planets in orbit around them. And this is a little misleading because, we're not going to see like bands on a Jupiter-like planet, but we'll be able to see a speck of light and then finally study it. And I have, there are prototypes that we have in the lab. This is 3 of us on the team here with one of the petal skeletons, and this comes all the way down here. That ends down there. So these things are this is one of the engineers that we work with, brilliant. Engineers just save the day with everything. So this is one of the Starshade prototypes that they're working on how to deploy that. And then I have finally here a video of this thing deploying. So these are all just little miniature versions of it, and this thing is opening up, and these guys are making sure the cables are all where they need to go and stuff. You're not going to have people like that running around in space, so we're going to have to figure out how to make it do that on its own. But we think we can do it. And at the end of all our searching, we arrive back at where we began. Hopefully in the situation where we've begun to explore the nearest planetary systems, we've started to know something about whether there could be habitable planets around them and what those planets are like, and just the sheer variety that is out there. The variety appears to be endless. And then, at the end of all this, we just gain a better sense of ourselves and how we fit into the big picture and how rare and precious we are. And I have a feeling that when when we begin to discover, even if I could generate a long list of habitable planets that I know are habitable with water, and maybe some of them have life, even then, I would say that no, there will never be another Earth. There will never be a twin of our own planet. It's irreplaceable. There are too many things about this world that make it just, I don't know if I should say, that the Earth is made for us or if we're made for it, but we fit together. It's a system and we're part of it. So I wanted to share this in the end. This is from Carl Sagan, one of our favorites.
We were hunters and foragers. The frontier was everywhere. We were bounded only by the earth and the ocean and the sky. The open road still softly calls. Our little terraqueous globe is the madhouse of those 100,000 millions of worlds. We who cannot even put our own planetary home in order, riven with rivalries and hatreds, are we to venture out into space? By the time we're ready to settle even the nearest other planetary systems, we will have changed. The simple passage of so many generations will have changed us. Necessity will have changed us. We're an adaptable species. It will not be we who reach Alpha Centauri and the other nearby stars. It will be a species very like us, but with more of our strengths and fewer of our weaknesses. More confident, far-seeing, capable, and prudent. For all our failings, despite our limitations and fallibilities, we humans are capable of greatness. What new wonders, undreamt of in our time, will we have wrought in another generation and another? How far will our nomadic species have wandered by the end of the next century and the next millennium? Our remote descendants, safely arrayed on many worlds through the solar system and beyond, will be unified by their common heritage, by their regard for their home planet, and by the knowledge that whatever other life may be, the only humans in all the universe come from Earth. They will gaze up and strain to find the blue dot in their skies. They will marvel at how vulnerable the repository of all our potential once was, how perilous our infancy, how humble our beginnings, how many rivers we had to cross before we found our way.
Thank you.
Dr. Turnbull, I think we've all had now our astronomy lesson. On Tuesday we had our engineering lesson, and yesterday was music and adventure, and today we are out in the stars. And now we know why we have to take care of this Earth so very much, and we appreciate your enlightening us on that.